The broadcast is now starting. All attendees are in listen-only mode.
Yes, please go ahead.
Okay. So, hi everybody. My name is Ajay Bansal. I'm an assistant professor here at Arizona State University. And today in this webinar, I'll be presenting on knowledge representation and reasoning for artificial intelligence. So I plan to offer a course over summer in the month of July. The location has to be decided yet. And so this presentation, this webinar is an overview of that course. Um, so So this is the outline of my talk, where I'll start with a little bit of introduction to AI, because I believe the audience not necessarily is from computer science or AI background. And so I'll give a little bit of a background on AI, and then we'll talk about the specific approach to AI known as knowledge representation and reasoning. And then what are the various challenges that this particular area or approach of AI faces currently? And then what are the various approaches that have been used to overcome those challenges in the past? And during covering all this, I will be giving numerous examples to highlight some of these topics. And then in the end, I will talk a little bit about the course that I plan to offer, what are the goals for that course, and what are the various topics that I'll cover in that week-long course that I'll offer. So starting with AI, there's always been very challenging to define what intelligence is, and especially what artificial intelligence is. And so after a lot of deliberation, I think the intelligence is defined with human intelligence as the benchmark. And so the AI systems in that way can be put into four major categories. So one is a systems that think like humans can be called artificially intelligent, and then you can have systems that act like humans can be called, or systems that think rationally, where rationally means always taking the right decision, or the goal is to take the right decision versus a human decision. And then systems that can act rationally. So quickly, what the difference between these four categories are: systems that think like humans will actually have a mechanism in which they would mimic the process by which humans think. And so cognitive science deals with this category of AI systems, where they try to mimic the neural system in the brain, and try to produce a system that can mimic human thinking. And then systems that act like humans, acting, now it doesn't matter whether you are really thinking or not, but you have to behave or act like humans. But then there was some thought there that what if an AI system is more capable than a human? So should it still act like human when it is able to perform large calculations? Should it still show that it's not able to do it outside the capability of humans? And so then they decided that no, I think why limit the AI systems, and so we should make them think or act rationally rather than make them think or act like humans. And so mostly these days the AI community has accepted that the systems don't necessarily have to think in a certain way, as long as they are able to come up with a good decision and act rationally. And so most of the AI community accept the last definition, that AI systems should be created in such a way that they can act rationally. So with that definition in mind, we'll proceed. The AI. So here, the AI progress towards intelligence has been that it started actually in 50s with John McCarthy coining the term at Dartmouth, the artificial intelligence. But over the next 2-3 decades, they came up with rule-based systems, which were called expert systems, and were very popular at that time. And then later on, they added reasoning capabilities to it, where systems like Deep Blue could dethrone the world chess champion Garry Kasparov. And so with reasoning, they could do much better than compared to simple expert systems. And then later on, they started getting into the perceptual tasks of, say, speech recognition or image recognition, and that came pretty later. And so in the first two things that I mentioned, expert system and reasoning systems, they were mainly dealing with knowledge representation and reasoning technologies. but those were limited and could not do the perceptual task of speech recognition or image recognition, because the knowledge that speech recognition or image recognition deals with is very hard to represent. And so machine learning techniques came into play, and then they started getting some success in those tasks. And so currently, the goal of AI, the big goal of AI, is to connect reasoning with perception, and so somehow build the bridge between knowledge representation and reasoning systems and machine learning systems. Now, deep learning has become very popular now, and a lot of things are being done in deep learning, but these are very orthogonal approaches to AI. They both produce intelligence, but they're very hard to connect with each other, and that's the current goal of the AI community, to see if these, or the capabilities of one or the other could be put together, or if there is a bridge between the two that can be put together. And so the goal of knowledge representation and reasoning community is to see if we can have more success in say common sense reasoning or perceptual reasoning, which is hard in this domain. And so if you notice the contrast here, that if you see humans actually master perception before they get good at reasoning tasks. And so we have a very renowned AI faculty at ASU. His name is Subbarao Kambhampati, and he was the president of Triple AI last year, and for the last 2 years, I believe. And then he actually noticed this, and he has made his research is in human aware AI systems and planning. And there he realized that AI progress has been the opposite of how humans progress. And so babies master perception much before they get good at reasoning tasks, but AI did it the other way. So the two approaches have been that should we think rationally versus act rationally, and should we use symbols versus neurons in achieving intelligence? And so brain clearly uses neurons, whereas symbols, human knowledge has been codified in symbolic fashion in the past. And so which one should we start with? And that gave the two orthogonal and very popular approaches to creating AI. And so in the past, Herbert Simon, Alan Newell, the pioneers in AI, have thought that a physical symbol system is sufficient for general intelligent actions, whereas Jeff Hinton, who made deep learning so popular now, he believes that symbols are just there everywhere, but they may not be that useful. And so he has his own approach. And so there's this two approaches have been orthogonal, have been, I don't want to say that there's a fight between the two, but they basically AI is, they have been successful in different tasks. And then we want to see which approach can be taken further to solve some of the problems that I'm going to present now. So my focus is more on the symbolic representation side, the knowledge representation and reasoning side of things. And so we understand knowledge as all kinds of facts about the world, something that is necessary for intelligent behavior. And so rather than thinking what is knowledge, we actually consider representations of knowledge and think about how we can make use of it in creating intelligent artifacts, which is the reasoning side of things. So knowledge has to be represented, and then you can reason with it. And so let's look at these two terms separately. What's the difference between representation and reasoning? And so some of the MIT folks have defined knowledge representation as a surrogate or a substitute for the thing itself. So the actual thing is represented in such a way that we can determine consequences by reasoning about the world or that entity. And so another definition could be a set of ontological commitments where we kind of represent the worlds in different terms and see if we can create a hierarchy or taxonomy or ontology of those terms with the idea to understand it better and represent the real world better. Then we can think of knowledge representation as an efficient computation mechanism where some reasoning can be accomplished. And then it's also a medium of human expression, a language in which we represent things about the world. Now, so the idea here is that if A represents B, then there has to be, like, A stands for B. But what's the point of using A when we have B? And it is because A is usually more easily accessible than B. And I'm going to give some examples to highlight what these are. And so we are interested in symbolic representations, and these are representation of propositions or truth statements that are believed by some agent, or that also represents the knowledge that we are trying to encode. And so what's reasoning? Reasoning is the use of these representation, these symbolic representation, to derive some new knowledge or some new statements. And while these statements are abstract objects, you will see in the next example that if you make a representation out of these statements, these are concrete things that can be easily manipulated. And so we'll look at a simple example, a simple problem of representation and reasoning here. This is a popular problem that many might have come across over many years that in their lifetime. And so in this problem, there's a man who lives on the east side of a river, and he wishes to bring a cabbage, goat, and wolf to the other side of the river. However, his boat can only hold himself and one of the things. And then there are rules that you cannot leave the goat along with the cabbage and on one side, because the goat will eat the cabbage, or you cannot leave the wolf with the goat because the wolf will eat the goat. And so in what order should he take the items to the other side to be successful, that he doesn't violate those constraints? And so if you think about it for a minute and see it's an easy reasoning problem to solve. But to automate the whole process, if to make a computer solve this problem, where do we start? So I'll give everybody 30 seconds to actually think before I present the answer. And so again, it's an easy problem, but where do we start? Oops. Okay, so I hope everybody got a chance to think. And I think the challenge, if you thought that there is a challenge in the starting, and the challenge is because we don't see a clear representation of the problem. These are abstract statements that need to be concretized in such a way that we can reason with those concrete statements, so we can do reasoning on it. And so one way to do the representation I'm going to show, so this is a simple reasoning approach for solving this problem by trying all possible combinations, but then we need a representation. So what would be an appropriate representation for this problem, or the knowledge presented in this problem? Now, there are many things that are relevant to our reasoning, and there are things that may not be relevant to our reasoning. For example, the age of the man, or the color of the boat, or the population of the village. Those things are not needed, but then there are things that are relevant. And with that relevant things in mind, the only thing we need for our reasoning, we need to represent where each particular item is at each step of problem solving. So currently they're all on the east side. Finally, they need to be on the west side. And at any time during the whole process, where each item is. That's the only relevant information that we need for reasoning and to be able to solve this problem. And so to represent that, we can use a sequence of the objects that we care about. And so there's only 4 objects whose position we care about, and so we can have a sequence of the location of those 4 objects. And so if man is on the east, the cabbage is on the west, and goat and wolf are also on the east, then this presented in the sequence that you're currently seeing can represent that particular state of the problem. And so once we have this representation, now things become very easy. Now you can easily see what's the start state of the problem. And the start state is that everything is on the east side. And where do we need to get to? We want to get to everything to be on the west side. And now our reasoning is basically whatever is allowed at every step, we take those actions and then see if we can get to the west side. And so the start state is all east, the goal state is all west, and we want to get there without encountering any invalid states where cabbage and goat or wolf and goat can be together. And so once we have that representation, again, the process is pretty simple. You just so at this point, there are three options. The man can take the cabbage or the goat or the wolf, and the first and the third is invalid state because you don't want that. And then there's only one valid option, and so you move on from there. And then now at any action you take, see if you've solved the problem. If you have not solved the problem, then you keep doing the same thing, and then you have more states that you can generate from that. And then so man rows back alone, that's a valid state at this point, but the goat would get you back to the start of the problem, and you don't want to do that. And so you keep doing it, and now with certain moves, you can reach the goal state. So the point here that I'm trying to make is that for every problem, this is a very simple problem, but even for a simple or complicated problem, you need a representation before you can start reasoning or trying to solve that problem. And once you have that reasoning, then in this particular case, for example, the reasoning for generating the goal state from start state actually translates into the solution of the actual problem, because the transition between state has a corresponding action. And those sequence of actions is the solution to this problem. So that was a little introduction to AI and the knowledge representation and reasoning. But there are lots of challenges that the KRR community is currently facing. They have been successful in doing reasoning system, expert systems. But for example, now that we want to deal with common sense knowledge, representation and reasoning with that has been challenging. And I'm going to present some more examples here. Then representing and reasoning with natural language has been hard because of various issues. And then if a KRR system has to do a trade-off between the accuracy of the result, the accuracy of inferences versus the computational efficiency, then it's very hard for KRR system to do that. And the example here is the example could be that in some cases we don't need a perfect solution. We need a suboptimal solution. Like for a lot of for a lot of NP-complete problems, for example, we don't have the optimal solution. It's very hard to find, but a suboptimal solution would work. But it's very hard to encode that in a KRR system where the system can do the trade-off of efficiency to accuracy. And then if you are dealing with an uncertain knowledge, if you're dealing with probabilistic systems or stochastic systems, and you don't have the complete information or uncertain knowledge, then the KRR community is facing challenges in representing these. And so here I'm presenting the work that is currently being done, focused on, and the future of KRR. And but there's a lot that has already been done by the KRR community and has been successful. So some examples to see. Let's start with the common sense knowledge. So if you look at this picture, the information is this is Annie and her babysitter. But then if you want a system to figure out which is which, a KRR system would not be able to figure out, because there is no information here telling which one is which, or the information that we have, the rules to encode, which can get you to that inference that the grown-up is the babysitter and the kid is Annie. That is not there. Another example could be a simple sentence like, if you stick a pin into a carrot, does it make a hole in the pin or in the carrot? Very hard for a system to figure out. Or Magellan the explorer went around the world 3 times. On one of his trips, he died. Which trip did he die? So take a moment and think about these 3 examples that I presented and see, why would a KRR system have trouble answering these questions? Like for a human, you can easily, these answers are obvious, but there is no existing computer program that can answer them in general. So, because to answer the question like the Magellan the Explorer went around the world 3 times and on one of his trips he died, we humans know the common sense here is that he must have died in the last trip, because after that he cannot take any more trips. But how would that common sense be encoded in a knowledge representation reasoning system? So the question is, can we get a copy of the presentation? So at the end, I can provide you with a copy of the presentation. That's not a problem. Okay, and so those were some of the examples of dealing with challenges with common sense reasoning, and I'll move on to natural language processing. This is something pretty obvious that most of you would know. Here is a small text that we can understand. And so I'll read it. The juiciest prize is to become the face of a luxury brand such as Dior or Burberry. To have any chance, a model must first have magazine shoots under her designer belt. And this fact allows fashion magazines to pay peanuts even for a cover shoot. And so we understand what it's saying, that for a model to be able to get to that point, they need to have some shoots, and because of that, they don't get paid very well for those cover shoots. But if a system has to process this, then you will see that there's only 2 words in here that are unambiguous. Rest all of them are either like ambiguous, but you can still break them into 2 into the blue ones are the ones with the most frequent meaning for that word, but the red ones are not the most frequent meaning. And so when you say the juiciest prize is if you see here, the designer belt doesn't literally mean the designer belt. It actually means that to have something in their portfolio or to have some value in the community, they need to do that. Peanuts doesn't mean the actual peanuts, but means that they pay very less, and so on. So it's very hard for an AI system to actually figure the meaning behind such a text. More simple examples could be like if you see the rules that cheap apartments are rare, and we know that rare things are expensive. And if we try to work with this, we can conclude the cheap apartments are expensive, which is absolutely not correct. And so it's hard to work with natural language because of the ambiguity that's present in the natural language. Now, this is another example where you can say, Mary knocked on Jane's door, but she did not answer. Now, if here, this is the pronoun resolution problem, where if the question is asked, who is she in this statement? So maybe we can figure that out. So Mary knocked on Jane's door, but she did not answer. And so we can have a rule in such a way that we can figure this out. But if we change the statement to Mary knocked on Jane's door, but she didn't get an answer, and now would the system be able to figure out? And then the first case, Jane is the resolution for the pronoun she, but in the second case, it's Mary who's she in the second statement. And so there is a whole challenge for this kind of statement, this pronoun resolution, and it's Winograd schema challenge, and I hope some of you might have heard about it. And that's the new Turing test that they are saying that if a system is able to resolve pronouns in these kind of sentences, then yeah, the system is an intelligent system. And so there are lots of such examples. If you Google Winograd schema challenge, you will find a lot of examples of such things, and a lot of people are working in the KR community to solve this Winograd schema challenge. And there's prize associated with it, and people have had success, but still, I think the accuracy, the state-of-the-art accuracy currently is around 70% of the questions in the question bank they have. Basically a system is able to answer up to maybe 70% of the questions and not more. So there have been approaches in natural language processing that try to solve some of these common sense and natural language problems, but their approach is based on patterns of words and not meaning. And so their translation approaches, their web search approaches, the examples are the Watson system that was used in Jeopardy and defeated the world champion Jeopardy. And then Siri that we use on our phones, it uses web search and voice interpretation, but it's tuned to questions that our cell phone users will ask. But these are all textual search-based approaches where there is no semantics that is being used. And the KR community actually wants to be able to use semantics to answer some of these challenges. So why is this hard? Like I explained, the facts are not stated explicitly in the text. So whatever fact you need to be able to reason and figure out a solution to a certain problem, they may not be there. Like if you stick a pin into a carrot, it leaves a hole, like this particular fact is not there in that sentence, the original sentence. Or the facts that grown-ups are usually taller than children, and if X is a babysitter of Y, then Y is a child and X is older than Y, which can infer that the taller one is the babysitter and the younger one is Annie. Such facts are missing and very hard to encode, very hard to encode all the common sense knowledge that's out there. It's very hard to put together. There is a system called CYC, Psych, that started, I believe, in '84, that has been collecting all the real world facts and have basically trying to create a common sense knowledge base with which some of these can be answered. And so, but still there are lots of challenges in this domain. So there are various KRR approaches that have been used over time and are still popular and then being used still. And so real knowledge representation, and I just got a message saying, so give me 1 second. I think there is. I'm not able to. Okay, I think I'll continue, and if there are any questions, I will. My mouse froze, and I'm not able to get to some of the things, but I'll continue with the presentation, and then I'll maybe take the questions at the end. And so, real knowledge representation reasoning system come in many varieties. And the main idea behind these approaches, main differences are the intended use of these approaches, the expressivity in these approaches, and the features that these approaches allow. And so, and I'll show some example to highlight this. But some major families here, families of system based on certain approaches are, the approaches are basically declarative or logic programming languages. They are very well suited for knowledge representation and reasoning. And I'll show you an example. This is the one that I'm going to highlight and show some examples for in this webinar. And then the rest of the approaches would be covered in the whole course. And so there are rule-based or production systems, constraint reasoning system, theorem provers, and semantic networks, frame-based representation, databases, deductive databases, relation databases, etc. Description logic, Bayesian networks are used to handle when you have uncertain information, and stochastic systems. And so there are tons and tons of different approaches that have been used for the various domains, and they differ in their expressivity and features that they allow. And I'll show examples for one of these approaches. So we'll talk about declarative/logic programming languages for a little bit, and I'll give an example to show how expressivity can make a difference in your knowledge representation and reasoning. And so before I get into declarative programming, I'll just compare it with imperative programming that we are used to or very familiar with. And declarative approaches have not been that popular in the past. Now they're gaining traction because they can be easily parallelizable, and so with multi-core architectures, etc., they are now becoming as efficient that they can be used in mainstream production systems. And so mainly programming paradigms or programming approaches can be divided into non-declarative, which is imperative programming, where object-oriented programming, etc. And then declarative programming is mainly functional logic and constraint programming. And so if you compare these two approaches, you will see that imperative programming focuses on things, on how to solve a problem rather than what exactly are you trying to solve. And so it requires the programmer to specify the whole algorithm. It's usually a sequence of statements that makes the algorithm explicit and leaves the goal implicit. And so, for example, if you look at this program, it is hard to figure out what this program is actually doing from just by looking at it. It's not a hard program. It actually computes. I'll give 30 seconds for everybody to take a look and see if you figure it out. So this is a program that computes factorial of n, but it's not very evident from the way it looks. Whereas in declarative programming, it focuses on what it's solving rather than how to solve, and requires the programmer to specify just the problem in some way, and the compiler figures out the algorithm, or the language system figures out the algorithm for it. And it's usually a sequence of definitions that represents the logic or the knowledge being used for the problem, and it makes the goal explicit and leaves the algorithm implicit. And so this would be a declarative program for factorial function, which is very easy to see that it's doing factorial. Now, to be fair, you can write a recursive program in imperative languages as well, but the goal is not to bash imperative programming, which has been very successful and very good, but just to show the approaches are very different. I'll give another example here. If you look at this script arithmetic puzzle where you have 8 unique letters, and these letters represent unique digit from 0 to 9, and so no two letters can represent the same digit. And so how would you assign, how would you find the digit that each of these letters represent such that this addition that is being shown makes sense? And so so the solution to this problem is this. It has a unique solution, and it's one of the famous script arithmetic puzzle. But how would you go about finding that D should be 7 and E should be 5 and Y should be 2 and so on? So take a moment to ponder over this, and then so in a imperative language, the solution would be maybe to start with a list of 10 numbers and then assign one to D, and then assign a number to E, and then add them up and do like the calculation of D plus E, and then do mod 10 to get Y and div 10 to get the carry for the next column. And then from the numbers that are remaining, you can take N and R and then add the carry and do the same thing and so on. So you would need the whole algorithm in imperative languages to do. But in declarative programming, you have formalisms where this can be treated as a constraint satisfaction problem, and the program is just this, what's being shown here. Basically, what you're saying is, okay, you have a list of digits, and those eight variables, SEND, MORY is the variables that you want to assign values to. And those variables have a domain from 0 to 9, and then they're all different. And then they follow this constraint that 1000 times S plus 100 times E plus 10 times N plus D plus blah, blah, blah. That constraint these variables follow. And now you say, okay, go find me those values for these variables. And the system will come back giving you that S is 9 and E is 5 and N is 6 and so on. So this is a pure declarative program where you are not providing anything for the algorithm. You are just representing your problem, declaring your problem, and focus is you can clearly see what is being solved here, and you are able to solve it just by declaring what the problem is, what the logic is, and no control is needed. There is no loop here. There is no eliminating variables from list, etc. here. There's no backtracking here. You just need to just list what you want to do, and then it gets done. And so such declarative paradigms, declarative approaches are very well suited for knowledge representation and reasoning, because you just need to represent your problem. They actually provide you a way to represent the knowledge that you're trying to represent, and then the inference mechanism that comes with these declarative paradigms actually ends up being your reasoning engine. And so to highlight a little bit more, a complete algorithm actually has two aspects, logic and control. What imperative programming requires you to do is to come up with both logic and control, whereas declarative programming only requires the logic and figures out the control on its own. And so this mechanism of figuring out the control on its own provides that reasoning engine that you need. And logic is your knowledge that you're trying to represent. You just need to use the framework to represent that. And so formal logic has been used for knowledge representation for quite some time now. It is the field of study of entailment, entailment relation, formal languages, truth condition, semantics, inference, etc. And so it's very well suited for KRR. So all proposition statements are represented as formula, and the semantics for that formula is the semantics that the logic provides. And so a logical system is a formal language and the semantics for that formal language. And they are a framework that helps with different kinds of reasoning. And so logic programming is such framework that is based on formal logic, and it is use of mathematical logic for programming, for computer programming. So in mathematical logic, you may have an implication statement like B1 and B2 and B3 and ... Bn implies H. But if you interpret this procedurally, which is to solve H, if H is a problem, if a problem can be represented by this rule, so solve H, you just need to solve B1 and then B2 and then B3 and ... Bn. And so a simple example is that if there is a rule saying if you press the alarm signal button, then you alert the driver of the train. And if you think of it as, okay, to alert the driver of the train, I need to press the alarm signal button. So it's basically treating an implication, a rule, as a procedure. And once you do that, you can do computation with mathematical logic. And so this is also called rule-based programming. Prolog is the most representative language. And here, logic is what you need to specify, and control is the different theorem-proving strategies that logic programming uses, which actually led to various extensions of logic programming. And so I'm going to show another example here to highlight different extensions of logic programming and their corresponding expressivity. And so to highlight that, the example I'm going to use is for the 8 queens problem, or the n queens problem, the general n queens problem, where on a chessboard, you want to place n queens in an n by n chessboard, or 8 queens on a regular chessboard, such that no 2 queens are attacking each other. And so again, take a moment to think, how would you solve this problem? So as you know, queens can attack horizontally, vertically, as well as diagonally. And there are 2 different diagonals, 2 directions to the diagonals that are possible. And so how would you go about solving this problem? It's a classic problem, and it has standard solution. But if you make the solution better with more efficiency, you would see that you need a formalism or a representation mechanism that would allow you to include that efficiency or whatever better algorithm you have. And so I'll show that in a minute, but before I show that, I want everybody to take a moment to think how to solve this problem. Okay, so one of the standard approaches to solve this problem is to start with an empty board, place a queen in the first column, anywhere in the first column, and then place the second queen anywhere in the second column, and check if it is conflicting or attacking the first column queen. If it is, then you place the queen in the next position. So to make it systematic, you can start with the first position always. So place a queen in the first row, first column, and then place a queen in the second row of the second column, and that's conflicting, and so move it to the third row in the second column, and so on. So as you place queens in the third column, the fourth column, you might get to a point where in the fifth column, you do not have any position left where you can put a queen such that it's not attacking the first four queens. And so then what you need to do is you need to backtrack to the fourth column and then move the queen up or down and to allow an open position in the fifth column. And then you move on to the sixth column in such a way. And any time you don't have any position in a column that you can put a queen on, you backtrack. And you might have to backtrack multiple columns before you can go back and place the queen. But this algorithm will ensure that you have a solution in the end. Actually, it's very interesting that 8 queen problems actually has 92 different solutions. And so you should be able to find one with this process. So this is an algorithm. And if you want to represent this algorithm, the simple traditional logic programming formalism would allow you to represent that algorithm. And I'll show you the program in Prolog for this. And so, by the way, this is what I just explained, that a queen attacks in all these possible directions. And so this is your 8 queens or n queens problem solution in logic programming, where you are defining a predicate saying n queens, which takes n and figures out the solution for you. It starts with it's a list of numbers, and then from that list of numbers, it tries to select a number for a queen or for a particular column, and then checks whether that queen is attacking whatever is currently on the board. And if it is not attacking, it finds a good number, then it moves on and checks and tries to fill recursively the remaining columns. And so what I just explained is the two predicates at the top, the n queens and the nqns. The nqns actually selects one queen for a certain column and then checks if it is attacking the current solution, which is the queens on the board. And if it is not attacking, then the backslash plus actually is the equivalent of not. So if it is not attacking any of the things, then it recursively places all the other queens on the board. And the rest of the predicate is for the attack and to generate the column list. And so that's not that that is easy to figure out. But here I want to go back to the problem specification, and I want to show an improved algorithm for this. So when I place a queen, for example, here, if you see, when I place a queen in the spot that is highlighted, which is the 4th row and the 3rd column, all those positions that you see the arrows are hitting, those are not possible. And so when I'm placing the queen in the 3rd column, I know that there is a certain position that is not possible in the 7th column or the 8th column or the 6th column, but I'm not able to make use of that information. And so what if I design an algorithm which, rather than using backtracking, uses what's called forward checking, and I want to include that in my program, then I would need a knowledge representation mechanism that is expressive enough to allow that. And so one way to do that is like we do in constraint programming, that instead of looking at this chessboard as like 8 columns where you can place, or 8 columns where you can place the queens, you think of each column as a variable with a value that it can take from a domain of from 1 to n. And then when you place a queen, so similarly, you will have 8 variables in the 8 queens problem, and each of those variables can take a value from 1 to 8. Now, when you place a queen in the 1st column, based on its position, it can have an effect on the domain of the remaining 7 columns or the remaining 7 variables. And so based on that position, you can prune the domain, or you can remove the invalid values from the domain of the remaining columns. And then you can move on to the 2nd column, and whatever values are left in the domain of the 2nd variable, you choose from that. And so if you follow this process, you do a much less number of backtracking to solve this problem. But the regular logic programming, traditional logic programming, is not equipped to handle a solution like this. You will have to, it will be very complicated in there. But then the extension called constraint logic programming, which is another knowledge representation formalism, actually has this mechanism built in. And so if you move to the second solution here, this is using the library of constraint logic programming over finite domain. In this one, actually, what you are saying is that the n-queen solution, you start with a list of 8 variables. So length qs comma n will generate a list of length n for the qs variable. And you're saying each of those variables has values in 1 to n. And you know that they all have to be different because you cannot have 2 queens on the same row. And then you just check for the safety of the queens. And so this actually, the way constraint logic programming works is that once you set those variables and their domains and the constraints on those variables, the CLP system actually takes care of pruning the domain and keeping track of what values are left in the domain. And you can make a very, very efficient algorithm there, and it can implement it easily. What I'm showing, what I showed in the previous slide and what I'm showing here, these are complete programs to the n-queens problem. If you try writing these programs in Java, C, C++, etc., they'll be much longer. But these declarative formalisms are meant to represent the knowledge and reason with it, and so these kind of problems are very well suited for such formalisms. But now if I add one more, so far we are able to handle the logic behind this problem and encode that logic or represent the knowledge. We are also able to represent it in a certain way where we represent it as variables and domains of the variables and then do domain pruning and try to get the solution using forward checking faster. But still this formalism is not expressive enough to encode what's not possible in this problem. So we can write all the rules by saying, okay, this is possible, this is possible, this is allowed, or maybe we can check that, okay, if this happens, then don't proceed, backtrack, and then, so we can only write things that are possible, but we cannot write things that are not possible in these formalisms. So there is an extension of logic programming or constraint logic programming to what's called an answer set programming. And what answer set programming can do is it can handle non-monotonic reasoning. In non-monotonic reasoning, you can encode things that are not possible. And so you're like, okay, in your solution, go find queen placements such that no 2 queens are attacking in the diagonal. You can directly write that. And so the next slide will show the same n-queens problem in the answer set programming formalism. And so you will see that these 4 lines or 5 lines, including the constant declaration, is a complete n-queen solution in answer set programming. It's a complete working program. The first line says that you can only have 1 queen in each row. The second line says you can only have 1 queen in each column. So there you are saying what is possible. And then the third line says that it is not possible to have 2 queens in the first diagonal, meaning in one direction of the diagonal. And then it says it is not possible to have queens in the second diagonal, second direction of the diagonal. And because here you are able to express facts of what is not possible, you are able to express the whole n-queens problem. So represent the n-queens problem so easily. And this is a complete program. You run it and it can solve it. It's really efficiently. In fact, if you try the first program, I'll go back 2 slides and show, if you try this, which is traditional logic program, you will be able to solve up to, I would believe, maybe a 50 by 50 on a good efficient computer, a 50 by 50 queens problem. If you go to CLP, you might get to 100 by 100 board or 100 queens problem. If you try solving it in ASP, these 4 lines are so efficient that on a regular laptop you can solve a 200 by 200, meaning a 200 queens problem in like less than a second. And so these formalisms, they are not only very expressive, but they're also very efficient. And so in my course that I'm going to, in my course that I'm planning to do over summer, I am going to cover these formalisms in detail and how we can encode and represent in these formalisms. And so there are many real world problems where KRR has been applied, has been very successful in scheduling, temporal reasoning, and planning, and VLSI design, etc. And then there are many companies out there that are using KRR to actually realize a lot of things. And so PsychCorp, actually not 1984 but 94, it was founded, and it's doing research and development and trying to come up with a big common sense knowledge base with which common sense reasoning would be realized. And then there are these companies like SOAR Technology that's trying to design highly human intelligent systems, and there are others that are doing that. And so at this point, I know I'm running a little bit short on time, so I will quickly tell you the course that I'm planning. The goals of the course is to provide an overview of existing representational frameworks developed within AI, and then the key concepts, their key concepts and inference methods that let you do the reasoning. And then we will see how you can represent knowledge or model your knowledge in these formalisms or framework. We'll also try to understand the principles behind different knowledge representation reasoning techniques. I usually teach all my courses with this discovery-based approach where I try to, rather than telling my students that rather than just telling them what it is, I try to create a situation in which we end up discovering the formalism or technology. So I'll follow that discovery-based approach in this course as well. And then being able to read and understand research literature in the area of KRR. So I'll try to cover some of the pioneering research as well as some of the current research in this area. And then the goal is that you should be able to complete a project in this research area. And so the topics that I'm going to cover is general knowledge representation issues. Some of them I discussed today, and I'll cover them in more detail. And then logical agents, the agents that follow reasoning in first order logic or non-monotonic logic and reasoning, like I mentioned, answer set programming today, modal logic, semantic networks, and knowledge representation for semantic web, etc. Then we'll talk about rule-based agents. We'll talk about probabilistic agent that uses Bayesian networks and other probabilistic knowledge representation reasoning mechanisms. And then we'll also look into that how can you create intelligence without doing representation and reasoning. And so at this time, I am ready to answer any questions that are there. I'm going to end the slideshow, and then I hope I'm able to click. Yes, and so I see a few questions, and I'll try to answer those. And so here I see left hand and right hand use is seen in the picture. Allow right hand of child which has lesser grip against left hand of the elder babysitter. I think the idea here is that that you are able to figure out a way to write a rule that will allow the system to figure out who's who. But what I'm saying is that what I was trying to point out is that such rules are specific to the picture or to the knowledge that you're dealing with. How do we generalize this, that these rules can come up on their own and we can answer the questions? So the other question that I received is, what are the different coding languages? What are the different coding languages can approach for AI programming? So I did show the declarative programming paradigm is very conducive to AI programming, because AI systems, if they are rule-based, these declarative programming, the logic part actually easily encodes those rules. And so languages like any language in functional programming, like Haskell or ML or Lisp, Scheme, etc., are very, very conducive to AI programming. Also, the newer languages like Scala and even Python and Go has a functional component built in. And so if you use Python and Go, you can use the functional programming aspects of those languages to encode AI, do AI programming. And then on the declarative side or the logic programming side, you have Prolog, which there are different implementations of Prolog with different capabilities. And so Klingo, for example, is a very well-known system for doing non-monotonic reasoning, which is answer set programming based. And then you can have 6DIS or SWI Prolog to do the regular Prolog programming or the constraint logic programming that I've shown in this presentation. So the next question is, what are the basic knowledge /skill required to work in AI? And so AI is very, very broad. Like I was saying, there are two main approaches to creating intelligence in the AI domain. You can do that using representation of knowledge and reasoning with it, versus you can do the more or the data driven knowledge, where you don't know the rules or the representation, but you have tons and tons of data, and you can do some machine learning to create some knowledge out of that data. And so depending on which side of AI you want to work in, you will have different skills that you would need to learn. And so in this course that I'm planning to teach, I would cover the KRR side more, but I will highlight some of the skills that can be learned for the machine learning side as well. And so then the next question, what are the major domains that are suitable for implementing AI? So one simple way to look at AI is to see it as a decision-making process. And so the main goal of intelligence is that we are able to make the right decisions in different situations and different contexts. And so so the decision-making domain, anything like planning requires decision-making. Any sort of, I would say, expert system requires decision-making. Any sort of reasoning system requires decision-making. These are self-driving cars. They, in here in US, many companies are trying that out. And so there are tons and tons of decisions that those self-driving cars have to make. And so all those domains are suitable for AI to pitch in. So does AI concepts work to solve civil engineering problem? That's a very good question. I think AI concepts can automate any decision making. Now, when I say any, meaning it has the potential to do it. Whether we are there yet or not, we don't know, but AI can automate any decision making in any domain. And so in civil engineering problems, if there are things that I don't know the details of the domain, but if there are calculations, if there are things that needs to be done, not like straight calculations, but based on the data that has been collected over years, if there are certain patterns that you want to take out in that domain, then AI can help. And so any decision making, like I said, AI has a potential. Whether we are there yet or not, that's a different story, but it can be applied. So is the course offered online? What's the duration, start and end date requirements? So this course is in plan. It has not been decided yet. Once the venue is decided, I would be informed. It would most likely, if it happens, it would most likely be in the 3rd week of July. And then whether it will be online or not, I'm not sure at this time. So then the next question is link/difference between AI, machine learning, and deep learning. And so that's again a very, very good question. AI is the broad field, and under AI you can have, like I was saying, so I'll give a simple example here to highlight the difference between reasoning versus perception. So if we notice, and this example is really simple, but it drives the point, I believe. So if you see, when a baby is born, a baby very quickly, within a month or so, starts to recognize its parents, right? And so if a stranger picks the baby up, the baby can cry, versus if a parent picks it up, the baby does not cry. And so the baby doesn't have a concept of parent. The baby doesn't have a concept of stranger, danger, and all. How does the baby shows that kind of intelligence? And so that's a perceptual intelligence. That's like a data-driven intelligence. The baby sees the mother's and father's face every day, many, many times, and it knows somehow, even though it doesn't know what safe is, it knows that it's happy in those situations, and so it shows signs of intelligence there. But say if this baby never met its parents, and say was taken away for some reason, and say when the baby goes to school and all, it becomes a kid, and say it's 10 years old, and now suddenly the baby finds the parent. And so the baby has never seen, there's no data for the baby to know that, okay, so and so is my parent and I'm safe with them. But the knowledge that parents are usually safe, and parents, the rule that if I meet my parent, I should feel safe, kind of a thing, does not require any data. There is no learning that needs to be done, because that knowledge is represented in the kid's mind, and so it can be applied right away without any prior experience. And so that's the difference. Again, like I said, it's very, very simple example, but that's the difference between what machine learning does versus what knowledge representation and reasoning does. Now, not everything can be represented, and in such situation, machine learning comes to rescue. For example, if you were to teach a kid how to recognize a cat without showing the kid any picture of a cat or any cat, original, like live cat, how would you do it? It's so hard to explain in rules or terms that, and it's so easy to just show a picture of a cat, and now the kid actually can recognize other cats. And so there are domains where it's very hard to represent all the knowledge that's needed. For example, a self-driving car, it's so hard to represent every possible situation that the self-driving car would be put under. And so it's very hard to represent and reason with it. Whereas if you collect the data over certain time, that how humans react to certain situations, with that data, you can create a model that will help the car drive itself. And so there are a lot of domains where machine learning and deep learning have been highly possible. Deep learning is a specific way of doing machine learning. And so this is a long answer to this short question. So AI is the broad field, and under AI you have knowledge representation, reasoning, and machine learning. Under machine learning, you have many different approaches, and one of them is neural nets based approach, and that's where deep learning, that's what deep learning is. And so those are the differences in these three concepts. So at this time, I see there are some more questions. Let me see. For analyzing videos and take decisions, how can AI help? Scenario online learning. Sure. So the same thing here. Depending on what approach you take these days, image recognition is very successful. And so if you break the video into frames and you can recognize the objects, and if there is a relationship that can be created between frames to frames of videos, I think it can be used to analyze videos. Here at ASU, one of my colleagues, he came up with a system to do invigilations of exams, an automatic invigilation. And so a student would actually, while taking an online exam, would record himself or herself while taking the exam and send the video. And the system can actually take the video and put checkpoints where it believes that student may have violated any integrity policies. And so, and then the instructor can just go check those the video at those checkpoints, and then can decide if the student is guilty of any academic integrity violations or not. And so so that's an example of where AI is able to help with making the decisions for the integrity violation, and is able to analyze the video. So, and again, I appreciate the comment that the talk was informative, encouraging, motivational, and simple. I like to keep all my presentations simple. I believe very strongly in the content, in the power of simplicity. And so the examples I like to keep simple, but in the whole course, slowly we will get to the complicated stuff, and I'll try to make them as simple as well. So hopefully some of you would get a chance to, or all of you would get a chance to join the course if it happens here. All right, at this time, I'll thank you everybody for attending the webinar. And if there are any additional questions, please feel free to reach me at my first name dot last name. So it's AJAY dot my last name is BANSAL at asu.edu. And so again, it's ajay.bansal at asu.edu. All right. Thank you, everybody. I hope you guys, you have a great day ahead.
Thank you, Dr. Bansal. Uh,